How does it look? Maybe we can turn it off.
How do I look?
No. Oh well. Okay, so, well, welcome to this first event of the Center for Computational Intractability. As you all know, we got a grant to set up this center and to study intractability that includes a fairly broad variety of topics. This center is going to be functioning for at least the next 5 years, and we hope forever. And it's a joint endeavor of Princeton, IAS, Rutgers, and New York University. And as part of the center activities, we'll have a lot of seminars. There'll be some every week. And this monthly meeting, which is about 6 hours, the first Friday of every month, unless if announced otherwise, but that's the default, first Friday of every month. So you can put it on your calendars. And the format of these meetings is going to be similar broadly to what we have today. Namely, there will be some public part of the presentation, not always about public key cryptography, but open to the public, which we'll also videotape and put on the web. And so this will be some kind of a this public part of the presentation will be some kind of an introduction to some topic that we're working on. And normally when we are working on a topic, maybe half the team or a third of the team is already an expert on it, and the others are not, maybe. And so this public part of the presentation is supposed to bring the rest up to speed on that topic. And then in the group meeting part of these get-togethers, we will brainstorm about some research, okay? And that'll also be led by 1 or 2 people, but everybody's invited to join. Now, I mean everybody in the group. Now, I wanted to say a few words about the collaboration policy and so on, okay? So in a group like this, I'm talking about the part where we brainstorm about open problems. The expectation is that if somebody presents an open problem that they're working on, and they do it in this group setting, I mean not in any kind of public setting, then the expectation is that if you want to work on it, you contact them, and maybe you'll set up some kind of collaboration that way. But if you take ongoing work like that and build upon it, you can't just go ahead and then publish it on your own. Okay, so you need permission from whoever presented it, or you need to talk to them at least about your ideas and set up a collaboration. Okay, so that's the collaboration policy and the ethics policy. Now, of course, this will not be ever black and white, but err on the side of being nice and friendly. Okay.
Yeah, we want to encourage people to talk about their problems. And
That's right.
Just be protected in this.
That's right. Yeah. So we want people to encourage people to be collaborative and open, and so since it's a fairly large group, it's fair that there is some understanding like this. Okay. So that's about it. It was about a 2-3 minute introduction, and we're ready to proceed with the day's business, which is Russell's talk about public key encryption, and then after that there's a lunch. Normally there'll be a lunch in this room, but today there's a CS department picnic outside. Is it at 12 or 12:30? Anybody remember? 12. Now, of course, at 12 o'clock there'll be a long line there anyway, so maybe we'll get there at 12:15 or something. And hopefully there'll be food for everybody. And after that, Boaz will talk about, that's after lunch, right? You're going to lunch,
yes,
yeah.
Yes.
And Boaz will talk about some ideas for some new ideas for public key encryption that he and Avi have. And then after that, we'll have some kind of a rump session, because Boaz will make a presentation, then we'll have some kind of a rump session discussing what he said. And then there's a session where some of you, 4 or 5 of you, will get up and talk about your work for 10 minutes each, just so that we get to know you. Often these are people who are postdocs or senior students. So
and we're hoping to rotate that throughout the year.
That's
so
right.
We should be able to by the end of the year, everybody should get a chance to talk.
That's right. So, because otherwise you wouldn't know each other. This way you know if you want information about some topic or want to collaborate on some topic, want a collaborator who works on some topic, then this way you know who all the other people in the group are. And after that, the 10-minute presentations, it would be great if all the PIs, that is the faculty who are on the grant, could hang around here, and we'll briefly go over the organizational part of all this. We won't do this always. We will delegate things to an executive committee, which will do most of the things. But for the first time, maybe if all the PIs could come, that'll be great. Okay. And am I missing anything? That's pretty much Boaz, right? Or Russell, I guess. I think that's pretty much today's business. Okay. So I'll hand you over to Russell.
Thank you.
Okay. So I'll take pictures of you. Sorry? I'll bring a chair.
So, just for the camera.
Yeah, we can do that next time.
Okay.
Is Russell going to use that chair since you're looking for
Oh.
No, I'll get it.
This will be, yeah. I'm not going to actually sit in.
No, I meant next to the
Yeah. Okay. So, you know, it's a little bit over 30 years since the notion of public key encryption was published, and maybe it was, there are stories that it was in circulation, in a classified circulation before that. 30 years ago, when it was first new, people thought, this might have some connection with complexity, especially with NP completeness, but I'm a little bit vague about what the exact connection is. Now, 30 years, so what I'm going to talk about is why we're still just as vague about what the connection is, but why we have very good evidence to back up that we're totally clueless. And so the main results are largely going to be of the form alibis for justifying our ignorance. And this is not I'm doing a survey on what we don't know, basically, and most of this is not my work. Whether it's my fault, you can ask for yourself. So, okay. So public key encryption is about the central problem of cryptography, which is secret communication. So in what we have two people talking on a network. And this network on this network there's an eavesdropper, and for the purposes of this talk, we'll make the simplifying assumption that this is just a passive eavesdropper who's listening to the conversation but not altering messages, and that even more simplifying, that the two people who are talking to each other actually have some knowledge about who they're talking to, which is often a very big deal when you're actually trying to arrange things. So, what do we mean you're talking to someone else? What is this other person thing? How do you define that? Anyway, so we assume that they know who they're talking to. Their only problem is that they want to talk secretly, but they're being eavesdropped on by some powerful adversary. Okay. Now, this has been studied for a long time, but the sort of more classical approach is to allow both of the people who are communicating some kind of secret code book or key that they know in advance. So some common information that they share in advance. And that's called, when you have this kind of code book, that's called private key cryptography or symmetric cryptography. The symmetry is between encryption and decryption using the same key. Okay. It's probably familiar to most everybody, but I want to make sure that I don't just skip ahead. Okay, so what if you don't share any kind of common knowledge? Then the first thing that you have to do to communicate secretly is agree on some kind of secret. Okay, and so what we want is some kind of protocol where the two people participate and end up agreeing on a secret. So we'll assume that they can make random decisions and then send messages back and forth. So a classical example of so secret key agreement was first talked about probably by Merkle, but sort of the classical example of a secret agreement protocol is the Diffie-Hellman protocol, and based on something a little bit stronger than the hardness of discrete log in a group. So you've got some group. Okay, so it's usually done modulo primes, but it actually makes sense in any group, and more recently people use groups like elliptical curve groups and so on. Okay, and what you have is some element of that group, and you have to be able to know how to do multiplication in the group. You give some element of the group, and you pick a large enough random power, and one person sends the other that random power of the group element. Okay? And the other person does a similar thing. Okay? Sends g to the y for some randomly chosen y. Okay? And then the secret they agree on is g to the xy. Because g to the xy can be derived in two ways. You can take the g to the x and raise it to a known y. Or you could take g to the y and raise it to the known x, and both give you g to the x times y. Okay. So this makes sense in any group, but it's not always secure in every group. And so exactly which groups are good for this kind of key agreement, for this Diffie-Hellman assumption, it isn't really clear, but there doesn't seem to be any generic way, and you can prove that there's no generic way in some sense, of going from g to the x and g to the y to get g to the xy in an arbitrary group. And it seems like it's this hard even in specific groups. Okay, so that was one of the first secret agreement protocols. And here Alice and Bob are interacting, and they get a secret, and usually these are called secret, sometimes called secret key agreement rather than just secret agreement, because the purpose of doing this early stages of getting one random secret is to use that as your key, as your common code book, in order to transmit messages more efficiently later. But there's nothing essential about using it for key to agree on a key, so we'll just call it secret agreement for this talk.
Can I ask a stupid question?
No, because there are no stupid questions, but you may ask a question.
Sorry, I came late. Well, the assumption here is that the eavesdropper can't see g of x and g of y as they're transmitted.
No, the assumption is that they can see g of x and g of y, but cannot see x or y. So the eavesdropper gets the conversation that's sent in either direction, but does not get the randomness that is used to generate this conversation. So, is one way to break this is to solve the discrete log problem, and from g to the x recover x, or from g to the y to recover y, but it's also not clear that that's the only way, and whether the Diffie-Hellman assumption that that is actually an intractable problem is equivalent to discrete log. It also has a rich history that I'm not going to, it's rich, it's complicated, I'm not going to go into it. Did that answer your question, or just postpone it, or?
If one wanted to go into it, is there a big preference?
Oh, I'm sure there is. Boaz, do you know?
Dan Bonner's physics has lost some papers from Dan Bonner's website.
That was the reference I could see.
Okay. So, what do we want from a secret agreement protocol? Well, so what in general the protocol is going to be is each of the participants has some private randomness, R sub A and R sub B, okay? And they determine from this randomness, they send messages back and forth, and that determines a conversation that's going to be a function of the two random tapes. And they both also individually output their guesses to what the shared secret is supposed to be. And we'll say the two guesses are SA and SB for Alice's secret and Bob's secret. So what we want for correctness is that with very high probability, when they say that they've agreed on a shared secret, they've actually agreed on the same secret. So the output of Alice is equal to the output of Bob. Okay? But then for security, we want that eavesdropper who gets to see the whole conversation, and I seem to have just slight typo here. There's no C after the comma there. From that conversation, can't determine the secret. And since we're saying that with high probability the secret is the same for both participants, I might as well define guessing the secret as guessing Alice's output.
You don't mind if you guess the first bit of the output?
So for this, I'm just going to say it's hard to get the whole output for this talk. Then for actual uses of secret agreement, we would want to refine the protocol so that it's what do you call it? Semantically secure, not just secure to get the whole thing, but there are standard ways of going from just if you use like Goldreich 11 bits, you can go pretty much automatically from this kind of security to semantic security. And there are also other notions of security like non-malleability and so on that you could add on top. But I'm not going to touch those. Because what I'm saying is we don't understand this. When we add more properties, we understand less, generally. Sometimes we don't understand when you can do vanilla secret agreement.
When minimum?
And under what assumptions?
But in some sense, this is the heart of the matter, because the other things
you can sort of add modularly on top, usually. There are some things that are not complete, but we have good technology for adding new properties on top of old properties. What we don't have is deciding whether we have the basic property to begin with.
So is it enough in this setting to just encourage SA and SP or
Yes. But, then I'd have to, if I just had them one bit, I'd have to say that with high probability means strictly bigger than a half. Yeah. Okay. Here I'm going to say, if there are multiple bits, then maybe with high probability means with all but negligible probability.
So this is due to Diffie-Hellman, the G2X.
So the protocol, the protocol that I gave before was due to Diffie and Hellman, unless someone in British security secretly did it and didn't tell anybody about it. But I don't think they had a complete definition of secret agreement. They had an example, but it was for later work to actually define what they were doing.
Was that pre-RSA?
Diffie-Hellman was about 2 years before RSA, and RSA was motivated directly by Diffie-Hellman. I mean, that's lineal descent. Diffie-Hellman also introduced the notion of public key cryptography, but had no examples, and that's why that's really what challenged RSA to come up with a good example, a convincing example. So public key cryptography per se is a very special case of secret agreement where you try to minimize the interaction. Okay? So in public key cryptography, we're going to have like just a 2-message protocol like we had before, but even more stringently, we want one of the messages to be fixed and done offline. Okay? So instead of having a new g to the x for every time we do the protocol, we want to have one first message that's a function of Alice's randomness. Okay? And we'll say that call that message the public key for Alice. And that's a public key in that Alice is announcing it to the world, maybe publishing it in a directory. If you want to communicate with me, use this public key. Okay? And then, so that part can be done offline. And then later, online, the person who wants to send Alice a message uses that public key somehow to send the secret message, a fixed secret that Bob picks in advance, to Alice, and perhaps flipping some more random coins, but using a deterministic. So Bob may be probabilistic, but once you've got the public key, that's fixed, and so you're just using that in a fixed deterministic way. Okay? Then Alice, okay, can store how she generated that public key, and maybe she doesn't store the whole thing. Maybe she digests it down to a secret key, okay, that she keeps private. And she uses her secret key and the message that Bob just sent her to figure out what the secret is, again, hopefully, because we might have some probabilism involved and there might be some small chance of mistake. So the situation clear? This is probably everybody's seen this, 20 times, but I'm trying to fix my notation because sometimes people use, I think a big assumption is that the standard assumption is that encryption and decryption be completely deterministic, whereas that's not actually required. And many of the public key crypto systems around don't have that property.
Actually, if you don't make that a requirement, then Diffie and Hellman also get the first public key encryption, right? Because it was 2 messages.
It was 2 messages, but it took El Gamal to sort of morph it into an actual public key system. Because in Diffie-Hellman, your first message has to be randomly chosen distinctly every time. And there isn't quite a clear way of putting a fixed secret in as opposed to randomly generating the secret.
So in this formal setting, is there any loss of generality in assuming that the secret key is just a random string? Which key, the secret key?
Yeah, so the secret key, okay, the secret key could be the whole random string, right? And I'm saying in general, we might as well just use Alice's randomness equal her secret key. So, but in practice, people tend to not want to save all that randomness. If you did a few tries to pick a random prime, you don't want to keep the false tries. You just want to keep the prime that you picked.
Also, the secret key usually has a meaning, like the factorization.
Yeah. So it's not without loss of generality. It's without loss of generality from a complexity point of view. From a pedagogical point of view, when you're presenting these crypto systems, it's usually not the thing to do. Okay, so if we just take that definition of correctness and security and map it down to this 2-round case, what we get is that what we want is the decryption using the secret key of the encryption using the public key of a secret should normally be the secret, with very high probability. Again, because we allow randomized schemes, it might not be probability 1, it might just be probability 99%. Okay? But on the other hand, we want that with high probability, the eavesdropper, what does the eavesdropper get to see? That first round, she gets to see the public key. In the second key, he or she gets to see the encryption using the public key of the purported secret and using some randomness. And so from that information that the eavesdropper knows, they shouldn't be able to recover the secret with non-negligible probability. This is just repeating what the definition was before.
Question.
Yes?
What's the significance of RB?
Okay, so we don't necessarily assume that encryption is deterministic. So you could encrypt the same secret in multiple ways, using different random strings. And there are a couple of reasons to do that. First is that by doing that, you can have your, we just defined this kind of weak notion of security, but as I hinted before, what we really want to do is get the semantic security, where even if you know the secret, you can't confirm that. Okay, and if you can't do that, if the attacker is also given the secret and it's deterministic, then there's no way that, from this situation, she can't confirm that. Just try to send the secret, and if it's the same message, then that was the secret.
It's clear when the secret is 1 bit.
Yeah.
The attacker would try encryption of 0 and
right.
1 and would know it's wrong.
Right. So that's one motivation to have it be randomized. But we'll also see some examples of encryption functions that are inherently randomized. Even El Gamal was a randomized encryption function, just because they couldn't quite get it to work otherwise. Okay. So what kind of examples of public key crypto systems do we have? Actually, not so many. And when you group, you could sort of, if you group them by, there are lots of variants of each kind of idea, but there aren't so many different approaches. So, there's the El Gamal approach, which I'm saying is basically taking the Diffie-Hellman secret key agreement and squishing it until it's a public key system. Okay, and it's already 2 rounds, so it's almost there. You just have to do a few small tweaks to it. So it's a little bit more complicated than that, but that's the idea. So there's El Gamal and all sorts of variants that are basically based on discrete log at various groups. And as I said, the security can depend on which group you're talking about. So you can have, whole books about Diffie-Hellman based crypto systems based on different groups. So, okay, and which groups are secure, and so technically they'd all be different encryption functions, but they're really just using this common idea. And similarly, RSA, that was the first encryption function, public key encryption function published, has all sorts of variants. There, the common theme is that you're giving what Alice does to generate her public key is describe some kind of group with a group operation, but where so she can announce which group people should do their operations in, but where only the person generating the group knows the order of the group. Okay, so the secret is usually the order of the group or some function of the order of the group. And the common thing is, the most common version is the group is multiplication mod a composite, and the order of the group determines the factorization of that composite. Okay. And so then what you use is that anything raised to the power the order of the group is just the identity map. And so if we've got 2 numbers D and E, that together multiply to 1 mod that order, okay, we can announce E and uses D as our secret key and have encryption be S to the E in the group and decryption be the message to the D in the group. And because of that generalized Fermat rule, I'm not sure exactly what it's called, probably has a name, that something to the order of the group is 1, that you get back the original secret. Okay. And again, you can look at variants of this in all sorts of different groups, and variants where you're using this order of the group in slightly different ways, like a Rabin scheme, but they're all essentially this idea.
In these cases, are you relying on some underlying hardness assumption?
Yeah. So I'm not saying that they're all equivalent. Right? In fact, the security really does depend heavily on which group you're talking about. You know, so Diffie-Hellman over elliptical curve groups is not the same as Diffie-Hellman mod prime, at least as far as we know, and depending on which elliptical curve you're talking about. So
you can apply elliptical curves.
But you're using the same rule for why you're able to do this. Have this trapdoor property. So it's a similar trapdoor, not similar security.
And there are elliptic curve versions of both of these.
Usually the first. I'm not sure. Maybe it's hard to. It's not in general easy to know how big an elliptical curve group is. So I'm not sure they can use RSA. The most of the ones I know. I don't, Boaz or
I don't know.
Someone.
But it's like the RSA stuff requires one extra thing, which is to know, to keep as a secret the order of the group, and the Elgamal or to really Diffie-Hellman doesn't require that.
Right.
It's not so easy to calculate.
So it's not so easy necessarily to generate a group where you know the order and nobody else doesn't.
Except using the composite.
In almost all examples, the hard problem in the first is a discrete log nature problem, and the second is almost always a factoring nature problem.
Okay. So another general.
Sorry. So early on, there were these ideas based on knapsacks.
Yeah. Okay.
Stuff broke down completely.
I'm just about to talk about that. Okay. So a lot of people early on came up with the following kind of idea, which would be to take some hard problem like knapsack or shortest code word and take an easy instance or easy class of instances of that hard problem and randomize that instance as in order to disguise it as a random looking instance. And a lot of people misleadingly said that this is a crypto system based on an NP-complete problem. We're going to talk about this general approach later. So in general, it doesn't give you the your complexity is only tangentially related to the NP-complete problem that you're starting with. It's only based on it in the wrong way, in that if people could solve the NP-complete problem for the parameters you're suggesting, they could break your crypto system. The reduction doesn't work the other way, that it's NP hard to break your crypto system, even in the worst case. So we're going to say, I'm going to discuss this.
Association.
It's, yeah.
By reputation.
Right. On the other hand, sometimes this kind of method gives you a perfectly usable public encryption, and a good example where it hasn't been broken after a number of years is the Michaelis crypto system that uses this methodology on the error correcting a somewhat random code, a random seeming code problem. Okay, and I'm going to talk about that more later. Another recent version, okay, that actually uses this idea of, in some senses, randomizing a weak instance, but does so in a very rigorous way, where you actually prove a connection between the worst case complexity of instances of a given type and the hardness of breaking your crypto system is the lattice-based methods. And since this was originated in work by Itai and Dwork, but there are a number of variants since then that have made the system more efficient or slightly tweaked the assumptions that it's based under, or both. So this is sort of a randomized weak instance, but with some theory behind it. But the theory is tantalizingly close to really connecting things, but I'll actually just briefly mention this. This deserves a talk of its own by someone who actually knows what they're talking about on this subject. I'll at least explain why it doesn't quite come up to giving a real theoretical foundation for public key cryptography. And then later in the day, we'll see a very different approach by two people over there.
It's not that different, but hopefully it's a little bit different.
Okay. So on the one hand, public key cryptography is our best. We at the Center for Intractability have this product, Intractability. Who wants it? Almost no one, right? It's like selling dirt, Who wants dirt? It makes things dirty. It's generally bad. So, who wants intractability? And cryptographers want intractability, and they're one of maybe two sets of people who want it. Okay? And the other set is all within this room, so they don't count. Okay, so they're our only customer. And they're a really good customer because public key cryptography is actually used, has important commercial benefits, like every time you do a credit card transaction or use a secured site, you're actually doing public key cryptography implicitly. And that's what your web browser is using, some version of public key cryptography. Okay, so and it's even mentioned in the original Diffie-Hellman paper that introduced this notion that maybe those complexity people can actually give us a foundation for this. Okay, and I keep on hearing references to a quote in Diffie-Hellman. The original paper is kind of hard to actually get a hold of on the net, and so I wasn't able to actually find that quote. But it's well reported that Diffie and Hellman were talking about some possible connection with complexity.
But it was before Cook and Clark, right?
No, it was, okay, so it was after, but not very far after. It was when, yeah.
That's what they said, is that now that we have a theory of anti-completeness, probably we can prove that P is different than NP and even support this hypothesis.
They said something,
yeah.
Slight stumbling, I don't know if they said slight, a stumbling block seems to be that NP completeness talks about worst case.
Yeah. And we'll talk about that again.
British intelligence guys also mentioned complexity in their classified documents where they also were thinking about these things.
Can you tell us that? Oh, okay.
But they mentioned that they want a book. There is an interesting new book on complexity by Van Zorgarten, I think, maybe,
yeah.
And they're waiting for it.
Okay, but the sad truth is, even though they're our best customer, we haven't really, as people trying to understand intractability, don't really have something reassuring to tell them. Okay. And in fact, all the, almost all the results from complexity are somewhat disturbing as far as the fragility of public key encryption.
Well, that just to make it what you said a little more positive, than a really large number of results in complexity, which you mentioned before, talking about what you can add on to the, to make your system much more secure, given these flimsy assumptions that you have to make on it.
Okay, but okay, so let me say, there is good news. I'm not going to talk about it. I'm talking about the bad news. Okay. So, one thing we could say is, well, we don't really have to give evidence, mathematical evidence that these encryption functions are secure. They work fine. Okay? But here's my, people have been trying to break these crypto systems implicitly for millennia. These factorization problems that's equivalent to the Rabin security of Rabin system, for example, that was studied by Euclid, So that's true. But what I want to say is what happened in our, mankind's understanding of these problems and ability to solve them is, up until 0 AD. Oh. So, I'm trying to put things on a big scale here. So like maybe until the ancient Greeks, people couldn't do it at all. They were like factoring 15 by hand. And then ancient Greeks, said, oh, now we can, factor 10-digit numbers if we could define what a digit was. But which is a little bit difficult in Roman numerals, but which maybe stalled progress for a while, and then sometime in the Middle Ages, we started actually having Arabic numbers, and that sped things up a little bit. You got from 20 implicit digits to 22 digits or something. And then you got to Gauss, and he did something astronomically bigger. But note that I'm defining digits on a log scale here.
So it's twice log scale.
So so he could solve problems that were 4 times bigger, which I'm just putting at a little bit.
It's twice log scale because already the algorithm.
Oh, that's true. That's true. I'm doing digits. Yeah. So and then and that's. Gauss was pretty much well ahead of his time, and there wasn't that much progress until about 1978. And why, coincidentally, the, RSA was published, and then just a few years later, we got improved factorization algorithms. And there were a couple of iterations of these improved factorization algorithms, and they made a substantial difference.
So, Russell,
and so that's sort of.
Was Gauss doing it entirely by hand, or he had like books, lookup books? Was there space complexity?
I think he was.
All sorts of
there are 2 theories about what Gauss used. The first is he did it entirely by, the power of his mind and on paper. The second is that he had grad students. I don't know. You have to ask someone.
Nothing has changed.
Yeah, I don't know.
Yeah. He was using what?
And what about idiots, savants? Autistic people.
I think we're making up mathematical history here. Is that? At least I was trying to, but that sounds interesting. I'm not sure whether that's. Did you really read that?
Yeah.
Wow. Okay. So, and then things take off, and, that's where we are today. And you know that if in the next 20 or 30 years someone actually manages to build a multi-purpose quantum computer, then from then on, progress just keeps on going. Okay, and, things go off the charts. So I'm projecting that sometime in the next 100 years, maybe someone will build a quantum computer unless it's somehow physically impossible, and then all of these problems will be broken. Or at least the first 2, the Diffie-Hellman style and the RSA style. Okay, so we really can't count on, just empirical evidence that these problems are hard, because their status empirically is changing day to day, and they're also all smart. Especially when you introduce a new crypto system, you can't count on empirical evidence, because the fact that you introduced it made it go from an uninteresting problem to a very interesting problem, especially if you convince someone to use it. Okay.
If somebody knew how to factor much better, they probably wouldn't tell you about it. Right?
Well, that's the question. Moni Noor said, what's the main purpose of using mathematically interesting problems as the basis for our cryptography? The main purpose is that, if I do something ad hoc, maybe some random hacker will break it. If I use factoring, then probably Lenstra will break it. And he'll publish rather than make a fortune. So I don't know. That's a psychological problem that I can't really deal with. You can just ask yourself, what would you do? Okay. So unlike, I haven't mentioned what the approaches are to private key encryption, but they're pretty much ad hoc, and the idea is to just do sort of random stuff to confuse people often. Okay? There are also more principled approaches, but again, I'm not going to, this sort of tangential. But I want to say, unlike the private key crypto systems, you notice that this common theme is that these public key crypto systems are highly mathematical. Okay? It isn't just, and it's not just because we want Lenstra to be the one breaking it. I think there's some reason why these problems, and I'm going to explain why public key cryptography may require more structured, more mathematical structure than private key cryptography. Okay, that's one thing we can, that's one way of making the results I'm going to talk about a little bit, at least seem like possibly helpful rather than just bad news.
More like number theory than
more like
combinatorial.
Yes, although there may be some exceptions that we'll hear about this afternoon. Okay, so having things be highly structured is both good news and bad news. Because things are highly structured, as Avi pointed out, there's a lot of techniques for adding utility on top of increasing security, notions of security, or adding utility on top of the encryption, the basic encryption functions. But also because they're highly mathematical, that provides powerful mathematical tools for breaking the system. Okay, and so we've seen the structure of public key crypto used in both positive and negative ways.
What is this adding utility? Could you give an example?
Identity-based encryption. Okay, so that's a good example. Another thing is like going from
Can you say it again?
identity-based encryption is a good example. There you're actually using very specific properties of specific encryption. So there's another reason to want to vary your group that you're working over, because they do while functions and pairings, yeah. And so you need all sorts of extra infrastructure in order to get that going. Another example is when simpler example is when you want to use it for something like oblivious transfer, public secret distributed computation. Oh shoot! When you're using zero knowledge to It's not secret sharing, but
So
oblivious computation. Oblivious transfer, and then you can use that to leverage up to oblivious computation to distribute, compute some shared function of individual secrets in a shared way without revealing the individual secrets. So for those things, often you use some homomorphic properties of the encryption. There are also possibly some generic ways, but they're not completely generic. Okay. So, so that I think leaves open, the following kind of fundamental questions. Okay. Are any of these proposed public key crypto systems actually secure, or is this just because we don't know how to break them yet? That they're actually can be broken, but we don't know how yet. Why are the proposals that survived, as opposed to the more ad hoc ones, the most mathematically elegant ones? Okay. Is there any complexity theoretic reason to believe that we can do public key cryptography? And finally, can we use complexity theory to design or evaluate proposals for public key cryptography?
This is all assuming P is different than NP. I mean, we won't be asking
right.
these questions.
That's true. Okay, and so since the minimum assumption is P not equal NP, sort of the ideal thing would be to really base a public key crypto system on NP completeness. And as I mentioned in response to questions before, this was sort of tried early on, and the kind of style of doing this basing gets you the style of randomize a weak instance public key functions. Okay, so an example of many examples were suggested based on knapsack, based on other even small variants of the following one that have been broken. Because it doesn't really, it only seems to base the actual hardness on this NP completeness, on this NP complete problem. Yes?
Theoretically say that a crypto system was broken. You mean theoretically broken or in practice?
So I guess either. So that's a good point. A lot of these, when I say that these things were broken, Daniele was telling me that a lot of them were broken in practice largely because there were attacks, but they're still exponential in one of the parameters, but the parameter wasn't picked large enough for anything approaching security in the original suggestions. And if you did, you would never want to even implement the crypto system. Never mind try to break it. That they had totally unreasonable notions of what the parameters should be.
But some of them could potentially be polynomial time and exponentially secure?
Some of them could be, yeah. But on the other hand, this style, okay, there are enough that were just broken, flat out broken, both polynomial time and you did on your computer, and you showed, I think there was a famous talk where Shamir started the talk by plugging in his computer, and by midpoint in the talk had broken, demonstrated that he had broken the encryption function during the talk.
Yeah, another talk the title was Breaking the XY Crypto System. And of course, nobody knew what the XY crypto system was. There were lots of people in the talk, and he's going, and eventually somebody raised their hand and was going to give him any two-author crypto system. He had a few examples, including one in which he was like Ram Shaman.
No, El Gamal is one. Yeah. No, it's actually just one hyphenated name.
Wait, Russell, we'll probably take a 5-minute break at some point, so if there's a natural place.
Okay. Well, so we seem to have stalled now. Who would like a 5-minute break now? No. Okay.
On the screen, why don't you?
Okay. So anyway, so here's the Michaelis encryption function that's based on this idea. So what you do is you take a hard problem, an NP hard problem, and then you water it down by taking a weak instance of the problem. So here in Michaelis, the hard problem is this error correcting code problem. It's a basic problem in error correcting codes. It's also NP hard. Okay? It's given a linear code defined by its generating matrix. So, and given a message that's within the distance of the code, where there is a code word being something in the range of this generating matrix. And we're working mod 2 here. Okay? And what you want to do is find a code, given a string, okay, find a code word that's relatively close to the string. And it's, I didn't say it here, but it's equivalent to actually find the code word or find the string that generates the code word, which is really what people want to do. But generally those are equivalent. Okay. So is the problem clear? So that's a fine problem. And it's not only a problem that's NP hard, it's also a problem where people want to solve it. And it's also a problem, a rare problem, where people want to actually solve random instances of the problem. Because random matrices are great codes. If we could have an algorithm that almost certainly decoded for random matrices, that would be groundbreaking news. Okay, so because it's such a fundamental problem, we at least believe that no one around has such an algorithm, because if they were, they'd be in that error correcting code community and they would have published it. Okay, so it's fairly fairly plausible that that's a hard problem for random matrices. On the other hand, these people in the error correcting code community do come up with specific codes that they can error correct. And one of those codes is the GAPA code. Okay, and I'm not going to say what the GAPA code is. One reason because I don't know, but the other because it's not really important for the crypto system. Just that this code where you can correct up to T mistakes in the error exists, and you can correct it with an efficient algorithm.
For every GAPA.
Yeah.
Yeah. So. Okay. So. Okay. So what you do is you say, okay, so random matrices are hard to error correct for. GAPA codes are an easy instance of that problem. Well, if I just say, oh, I can error correct GAPA codes, so can you, right? If I tell you it's a GAPA code. So what I'm going to do is make it look, I'm going to use as the GAPA code as my private key. The fact that my code is really a GAPA code, I'm going to use it as my private key, and I'm going to randomize it to make it look like a random code and then give it to you to send messages to me for. And the adversary only gets to see the randomized version, and hopefully they can't detect the easy kernel inside that randomized version.
So it's a randomized presentation.
It's a randomized yeah. So here, so what we're going to do is pick two matrices, and one is just going to be a permutation of the outputs of the output bits of the code, but the other is going to be a random invertible linear transformation. Okay, and I'm going to keep these two matrices as my private key and announce a public key that says, oh, well, first we'll do that change of basis, then apply that GAPA code, and then permute the outputs according to P. Okay? And then to send me a message Okay.
So M, capital M describes this new.
Yeah. So that's my public key. So when you want to send me a message, you pick an error vector that has at most T1s. You take the message that you want to send, you apply this new permuted GAPA code, or randomized GAPA code, to that message, add in that noise vector, and then when I get it, I'll first undo the permutation. That's easy. And then I'll error correct to get rid of that error vector. Note the important thing that makes it crucial that P be a permutation is that when we invert the permutation, we need that the inverted permutation of the error vector has the same Hamming weight as the original error vector. So that's a permutation of the indices, right? It's not a permutation of the space. Okay, so, or it is a permutation of the space as well, but it's not an arbitrary permutation of the space. So then I can error correct that, get rid of this permuted error vector, say what your, and get your message that you're trying to send me under this new change of basis that I know, and then I can invert the change of basis to get the message that you were trying to send me. Okay. So as far as, so this is a perfectly fine encryption function. In some sense, it's using this NP-hard problem of minimum code. It's using this practical problem of inverting random codes, but it's not really based on either of those two. Because the problem is that, we have this randomized GAPA code, okay? But a randomized GAPA code is not a random code. And it's not even close. And you can just do this by a counting argument. This permutation has L factorial possibilities. The linear transformation, there's 2 to the n squared possibilities. But